Hello, so in this video we're going to start to introduce this idea of something called a derivative, right? Which should be basically the core of this topic, right? Differentiation. It's a very important topic, and we're going to start to introduce it properly in this section here. So first of all, I want to revisit this example that I did in the last video. Okay, so I did go through this example in more detail in the last video, but I want to revisit it again because it's going to start to lead us to a very important idea. Okay, so what's happening in this diagram is we've got this curve y is x squared and a tangent at the point A. That's the red line, right? This red line here. And again, a tangent line is a line that touches the curve at a particular point. So if I was to, let's say, move this, hopefully it works nicely. Move my ruler here to match the tangent. There we are. Okay. So you can imagine just moving the ruler line so that it just about touches the point A here, right? So it's touching the black curve, and so then the gradient of the curve, right, the x squared, at this particular point, the gradient, so how steep the curve is at that point, is the same as the gradient of my tangent. And so with lines, because the tangent is a line, that'll just be changing y and changing x, right? That we know. And so that's the idea. So this whole section is to look at basically gradients of curves. Okay. So how steep curves are at particular points. Okay. And so far, and from G to C, you're used to finding the gradient by drawing a rough tangent line at a point. So we're going to use that same idea, right? Then this whole tangent thing. Okay, so then I did that. Then obviously I did changing y, changing x of this tangent line, and I got a gradient of 2. Okay, so the idea is that overall my gradient at A has to be 2, right? What we then looked at is this blue line here, right? This blue line A to P, right? This point P. So the line connecting A to P. And basically the whole idea was we moved this point P closer along the curve to A. So originally, if I'm going to get rid of this, originally P was at 2, right? P was at 2 roughly. And you can sort of see that here. So if I moved P to 2, so that's P's 2 roughly. When P's at x is 2, right? So when x is 2, that's where P is. The gradient from A to P, which is the blue line, right? So if I again move this ruler here, if I make my ruler match the blue line, obviously you notice the gradient is different to the tangent, right? But the gradient, the blue line, that's the line here, the blue line here, from A to P when P is at 2, right? X is 2, roughly, there, okay? So then the gradient was 3, okay? A to P when P is at 2. The gradient was 3. Then we moved P closer to A. Then we said, what if P is now when X is 1.5? So 1.5 would be here, right? So now P is there. Now what happens is, obviously this was the original blue line, right? So imagine my ruler, I'm moving here. My blue line, the original point P at 2, that was my blue line. Now when P's moved to 1.5 instead, getting closer to A, the line's going to be a bit different, right? It's going to be the gradient's going to shift a little bit, as so, okay? So hopefully you notice I had to change the gradient, right? So I've changed the position of my line, and that would be my new line there, my new line from A to P. Now that's 1.5 when P is 1.5, right? Now, what I did then is move P even closer to A. Now, what if P is 1.1? X is 1.1 on my curve. So 1.1 would be now about here, right? P there. So again, now with this new from A to P, now I need to move my curve, my line a little bit more, a little bit like that to compensate. And so with this new point, then the gradient is now 2.1. So when we move the point P of my curve right closer to A, so originally X is 2, then X is 1.5, then X is 1.1. The gradient is 3, then goes down to 2.5, then 2.1. Well, what's interesting is the gradient is 2. So it seems like as I get closer to A, where I move my point P around closer to A, the gradient starts to resemble the tangent at 2. I need to get to 2. Okay, then actually I move it even closer. Then I say it's 1.01, right? So remember A is just 1. 1.01 now is where P is. That would practically then be right next to A, right? If you imagine it there. So if I have to shift it just a little bit more, that sort of way, right? Now to reach, you probably can't even see the point now because it's so close together. But that'd be my new blue line from A to P, and then the gradient of this line is now 2.01, very close to 2. That's interesting. And then actually, if you look. Well, actually, my ruler now is basically matching the tangent line. So the gradients are basically starting to equal. The lines are basically the same, right? Okay, and so then we can theorise then that really, as we have a point A and then another point P, we move closer to A on the curve. So P was here, then P was here. Then P was here, then P was here, right? Closer to A, my line from A to P, the blue line, this line I've got here, it's basically matching the tangent at that point A, right? And so the idea is, eventually, when we have when we move our point close to A, then that matches the tangent, the gradient that we want, which is the gradient of the tangent. So we've got this other way then, basically, of finding the gradient at a point, say A, right? The gradient of a point on the curve. By considering this idea of moving another point on the curve, closer and closer to my point A, which I am interested in. Right, and so actually then, what happened was, eventually, well, instead of just... what we said is just effectively just add a number H on at the end, right? So we start at 1, right? Then we add a number H. So H is basically the gap between A and P. And so then the gradient in this case was 2 plus H. Now, again, what I'm talking about here, for example here, this gap H is basically the gap between A, which is when X is 1, and the X of P. So originally P was 2, right? So the gap would be H is equal to 1, right? So remember, originally when P is 2, which is quite far away from A, right? It's quite far away. The distance or the gap between A and P, right? A and P for X. So at A, it's 1 for X, and P, here it was 2. So then 2 take away 1 is 1. So my gap is 1. Then we sort of, and again, the idea is we make it closer to A, so we reduce this gap, we reduce this H value. So then when P is 1.5 now, well, the gap is now 0.5, so we add in another 0.5 on from A. Then when it's 1.1, then the gap goes to 0.1, okay, so we're adding a 0.1 from 1, where A is. Then eventually it gets to H is 0.01, okay. And so again, you see that the idea is that the gap H, right, from A to P, so again, this is the gap H, say when P is 2 up here, the gap would be H is 1, okay, again. So then eventually when we minimise the gap or make P closer to A, H decreases and then the gradient is getting closer and closer to 2. So we get a better approximation. Then what we said was eventually this gap H, what if we just left it as H? What if we just said 1 plus H? Don't even give a number for H. Then eventually we get this gradient of 2 plus H. Well, actually then you should notice 2, but that's the exact gradient of the tangent, right? Which is the gradient at the point A. But then if the gap is basically nothing, then when H just basically goes to 0, where P is basically right next to A, then we just get 2, which is the exact gradient. Well, there we are then. So now we've got to start to get this idea of moving the point closer and closer to a point A on the curve. We can find the gradient at the point in this way. Okay. Right, so hopefully that sets the scene for the idea of what we're going to be looking at, right? The idea that if we have a point A, which we want to find the gradient of, so if we draw the tangent at A, we get gradient of 2. Then we make points P also on the curve. Then if we move the point P closer and closer to A, then we get a better approximation for the gradient, right? And so there we are. Now, okay. What I'm then going to do is do the more generalised idea now. So, let me now consider. So hopefully that gave a good example of what's going on. But let's consider a general curve now. Let's say we have, I don't know, this curve here, right? Let's say we want to find a gradient here, and let's call that A, right? The point A here. Now A is xy. And then this curve, right, is a general curve. So I'm just going to call it y is equal to f of x, right? Some function x, some curve I'm plotting, any general curve. Now, at this point A then, obviously we said that the gradient we're interested in, really, is the gradient of the tangent at A. So it kind of needs to resemble, if I move it here, this is my tangent line, right? If I make it touch A, my tangent is going to look like this. And so if I was to compute the gradient of the tangent, that would give me the gradient of the curve at that point, okay? That's what I'm interested in. Okay, so then I said, well, we have a point P, right? And then the idea is I want to make P closer and closer to A to get a better approximation for the gradient between A and P to match the gradient of my tangent, okay? Tangent. Now, let me then just say that originally, let's say P's up here. Now, the coordinate of P, what I'm going to say is, I'm going to use this idea of H again, right? So, at A, it's xy, right? Or actually, not xy, but or A, x, and then f of x, because y is equal to f of x, right? Hopefully with me so far. So then I'm not gonna give a numerical answer. I'm gonna use this idea of H. So H being the gap then between A and P, right? H here, which means if A is x, right, just x in general, then P, the x coordinate of P, well, we're adding a H on, right? So it's going to be then x add H. And therefore, if I substitute this expression for x, right, my input is now x plus h into f of x, it will be f of x plus h. Okay? Cool. Hopefully with me there. Okay? So there we are. So hopefully you can see then that this idea of h is basically, I'm adding h on, right? H is basically the difference or the gap between point A and point P. Okay? And there we are. We get these coordinates. Well, then we're going to do the same idea. Then we're going to consider the gradient between A and P, right? If we were to do that, it would look something like this. But obviously we're not quite there yet. It's not matching my tangent, right? You can see the two lines I've drawn, they're not really matching the gradient, right? But that's okay at the moment. What can I say about the gradient of this line I've just drawn, right? So if I do that again, so the gradient between A and P, right? Or the line between A and P, right? What would be the gradient of this line then, right? And then to work out the gradient of this line, so the gradient of AP. So remember the gradient from A to P. If A again has the coordinate x f of x, and then P has coordinate x plus h, because again we're moving h away from x, or h away from A, and then f of x plus h. So then this gradient then of the line A to P, right, that I've drawn here again, A to P, right, hopefully you can see that from points A to P, the gradient of this line, that's going to be changing y and changing x. That, remember, because it's a straight line. Remember, straight lines is just changing y and changing x. Well, the change in the y coordinates firstly. Let's take P. At P, it's f of x plus h, right? That's my y value at P. Take away then the y value at A, which is just f of x, right? And then I'm going to do the same for x. So then the change in x values then, well, at P, the input is x plus h. And then subtract x for A. Okay? Okay, and I can actually simplify the bottom bit ever so slightly. Because if I did, well, it's going to be f of x plus h minus f of x over x plus h minus x. Well, the x's will cancel, right? X minus x is 0, so I'm just left with h. And so actually then I'm left with this expression for the gradient here in terms of x and h, right? Okay, so that is the general expression for the gradient, which means no matter what then, no matter what I choose to be h, no matter how far or close I want to move P to A, if I move, again, if I get rid of this, if I then move P to here or P to here, because it's already in terms of A and H, it will always, the gradient between A and P, no matter where I move P, it will always be this expression here. That will always be the gradient, okay, in the general form, okay, in terms of H and X. Okay, so then what I'm going to do is then, I'm going to redraw the tangent then, to make it very clear, right? Okay, let's try that. There we are. So that's my tangent. Now, what we're going to then experiment with then, obviously we've seen what the gradient is, right? The gradient is this expression here, right? What we're going to then do is look at, again, this idea of making P closer and closer to A. So P is originally here. If we then draw, so then if we then do the line from A to P, right? So obviously that's my tangent line. That's what I want to end up with. The line from A to P matching up with the tangent, right? To get me my accurate gradient. But then, okay, so A to P here, when P's quite far away, so the distance H is quite far from A to P, that's what my gradient line will look like, right? If you see my ruler here, that's what the line from A to P will look like. It's not really matching up the tangent, right? Let's say then we put P closer to A. Let's say P is now here, right? Okay, so then instead, so now we're going to need to shift the curve downwards like this. The line, sorry, downwards. So again, my point P is now here, so I'm matching up A with that point here I've circled. So it would look roughly something like that. So it's still not really matching up with my tangent line, right? Okay, so let's try and move P closer and closer to A. Let's say P is now here, right? So now I'm going to need to shift the curve, the line, sorry, down even more. Something like this. Well, it's still not matching the tangent, right? The red line. Hopefully you notice it's getting a bit closer though. We're getting warmer to the actual tangent line, right? The line from A to P. Okay, let's now consider P being very close to A. Let's say P is now here. Oh, let's say P is now here, right? Well, actually, then we're pretty much almost bang on. It's starting to very, very closely match the tangent line, right? We're very close to the tangent line, but we're still a little bit away from A. Let's try and edge even closer towards A. Let's now move our point P, let's say here, right? Pretty much knocking next door to A, right? Okay, so now so I have to shift it down like this. Oh, but there we are. Now it's pretty much matching the tangent line, right? We've got a very, very good approximation to A there, of the gradient of the tangent then. As we move P closer to A, we're now at this point where basically my ruler, my line connecting A to P, is basically matching the tangent. And then you can imagine, as we shift even closer to A, we'd have to move it like this a bit more. And then eventually is pretty much on the tangent line. So the whole idea is eventually what we want to do is this gap H, right? This gap H then, the distance from A to P, right? I want to make that distance, that H, as small as possible. Basically no gap at all. Because then eventually it starts to hone in on the tangent. And therefore the gradient is what I want, okay? Because my line from A to P is basically the same as the tangent. And so hopefully you notice there's a stark difference between P, which is like here, right next to A, and then originally when P was far away, right? So then if P was over here again, I'd have to look something like this. From A to P, it's quite a noticeable difference now, right? It's far away from the tangent. But if I make it the tangent basically at A, if I move a point basically close to A, so I'm basically drawing a line at A, it's then the tangent effectively, right? And so that's the whole idea then. I basically want to minimize my sort of distance, right? My distance H, right? My gap for the distance from A to P. I want to make P basically next as far closely as possible to A. So there's basically no gap. So I want H to basically go to 0, right? And then as you've seen then, like with the first example, when H basically goes to 0, there's no gap between them. We basically get the tangent line. And so therefore that's the gradient. Okay? So remember then, at any point P, right? No matter what value of P I choose, this will always be the gradient, right? But then as we've seen, we want to make this H, this distance from P to A, this X plus H, I want the H to go away. So then basically P is basically on A, right? So there's no difference between A and P, which gives me my tangent, okay? So therefore I want this expression, right? This tells me my gradient, right? But I then want this gradient, I want this H going to 0, okay? What we can say then is basically we want to make H then basically go to 0. And so what we say is as P gets closer to A, H tends to 0. This notation means H tends to 0. The H is getting closer and closer and closer to 0, which means P then is getting closer to A. And so as we've seen then, like with the previous first example as well, when my point P gets closer to A, we basically match we get the gradient that we want between the 2 points, which is also the gradient this here. So as H gets to, so basically what we want is that basically to put H is 0 into this expression here, effectively, right? And so therefore our gradient, right? Our gradient overall is going to be this expression, a to p, but when p is basically right next to a. So that has to be when the h tends to 0. So when the gap between a and p is basically non-existent, okay? We notate that then by saying something called a limit as h tends to 0. This lim stands for limit, okay? And we use the h tends to 0 underneath it, okay? So that means the limit, or lim, as h tends to 0 of my gradient expression here, okay? And that's it. So then my gradient at a is this expression here, okay? Overall, then, as we take as h goes to 0, then, so as my point p is basically extremely close to a, basically next to a, right? Then that gives me the gradient, okay? As h goes to 0, right? But again, I didn't really specify any particular value of x. So really, a could be absolutely anywhere. I could pick x is 1, x is 2, x is 3. No matter where on my curve, a could be anywhere because I haven't specified exactly what value of x I've chosen for a. A could be anywhere, it could be any value of x. So actually, this is the general expression for the gradient at any point on a curve f of x. So this is quite a powerful statement actually, because it's saying for any curve whatsoever, any curve f of x whatsoever, any point x whatsoever, we can then compute this sort of expression here to give me the gradient at the point, where I don't need to resort to sketching the curve, I don't need to resort to drawing a tangent or anything like that. I can just work algebraically with this expression instead, okay? And that's what we'll be doing in this section here, okay? Okay, so we're going to start operating with this expression here, and this is called what we call first principles, okay? This expression for the gradient of a function let's say y is f of x, is called by first principles. Okay, and so from this then, we basically will be able to, later on in the section, be able to come up with more ways of finding gradients of functions, okay? But this is basically the core, okay? This is the definition of sort of a gradient of a curve, right? So that's where it comes from, first principles, right? First principles, sort of like the most basic, default, sort of way of defining it, okay? So we're going to start to work with this function then, okay? So you don't necessarily need to understand the whole in and out of the derivation. So as you know, you should know differentiation from first principles. So you need to be comfortable with the formula, okay? Essentially, and you should be you'd be glad to know this will be in the formula book. But as you get used to doing more questions, this will become second nature. Okay, so you just pick it up anyway. So we're going to start with some questions then to look at this idea. Okay, and again, this is in the formula book. This is what it looks like. Okay, so make sure you're comfortable with reading that. But we're given this example then, and we're told a point A with coordinates 4, 16 lies on the curve with equation y is equal to x squared. The point A on the curve has gradient g. Show that g is limit as h tends to 0 of 8 plus 8. Okay, so it's quite a weird sort of expression, right? But we now know how to find the gradient using this formula, right? So we're going to work with that then. The gradient g, well, originally y is equal to x squared. That'll be also f of x is equal to x squared, right? And so therefore the gradient g is this formula here, okay? So it's the limit. So if I just copy it down, it's the lim, or the limit, right, as h tends to 0, of the expression f of x plus h minus f of x over h, okay? Right. We know what our function is, right? It's f of x is x squared. So if I then work with this then, so it's the limits h tends to 0, then f of x plus h, my input is not x, it's x plus h here. So if I put in x plus h in replace for x, it will be x plus h squared, not x squared, x plus h squared. Okay, then take away f of x. Well, f of x is just x squared, so take away x squared, all divided by h. Okay, so what can we do here? Well, we can expand the bracket, right? So lim as h tends to 0. And then if I expand this bracket, h plus x plus h squared, well, that's the same as x plus h. Then if I expand this, well, I get x squared, add hx, add another hx, will be 2hx, add h squared. So again, don't worry about all the weird h's everywhere. Let's just work with that. So we're going to get x squared and 2hx plus h squared. Take away our x squared here, all over h. And then actually, the x squareds here will cancel, right? X squared take away x squared will go to 0. So I can simplify the top bit. To get x squared to cancel, so I'm left with just 2hx plus h squared all over h. Okay, what can I do here then? I can factorise a h on the top, right? So h of 2x add h over h. Okay, well actually then I can cancel the h out. The h is out on top and bottom. So lim as h tends to 0 of 2x add h. Okay. But my expression is 8 plus h, okay? But I've got, what do I have here? I have 2x plus h. Well, actually then, that's the gradient at a, right? A is 416, so x is 4, okay? So then I'm going to substitute x is 4 into here. So that means my g, my gradient g, is going to be the lim as h tends to 0. 2 lots of x, that'd be 2 lots of 4 add h. Then if I do 2 times 4, I get 8 add h. And what do you know? There we are. We arrive at that expression there. Cool. So that's the whole idea, right, with this using the formula. The formula looks way more scarier, or way scarier, I should say, than it looks way scarier than how it actually works, okay? Because all we're going to do really is to substitute the function into my expression, and then things will cancel in this way. Right. Then part B says, now that we've got this expression, deduce the value of g. So deduce the value of the gradient g. Okay. Well, this is now gonna deal with this whole limit, right? This whole business of h going to 0. So lim as h tends to 0 of 8 plus h. But basically, the idea is we want to push h to 0, right? H we want to go to 0 because then my point P will basically be at A, right? So then the gradient will match the tangent. That's what we're going to do. Then we're going to look at just trying h is 0, okay? It becomes 8, then h, when it's pushed to 0, basically goes to 0. So it's basically 8 add 0 that we're left with. That would just be 8. Okay. So that then tells me then that the gradient g is 8, and particularly when, remember, it's at the point A. So when x is 4, right, at this point 416 on the curve x squared, at the curve x squared at the point A, the gradient of the curve, the steepness, is 8. Okay. Right. Okay. Right. We're going to look at another example now. Now we're asked to prove from first principles. So remember, first principles is my formula. Lim h tends to 0 of f of x plus h minus f of x over h. That is in the formula book again. That's first principles. Prove from first principles that the derivative of x cubed is 3x squared. Right. So what, again, I have function here. My function is just my expression, right? X cubed, right? So f of x is x cubed. Then we want to show that the derivative is 3x squared. Now, the derivative is the gradient, effectively, right? But the derivative is a bit more than just a gradient. The derivative is the gradient expression. It's the gradient function. You'll see what I mean after this example here. But it's a gradient function, okay? So obviously a gradient with straight lines, you're just used to changing y and changing x, and you'll just get a number out of that. But a derivative is a gradient function, so it's going to be in terms of x, and you can see that here, right? It's in terms of x, my derivative, my gradient, okay? We'll see more about that after, but for now, f of x is x cubed, then the derivative is, we notate it by this, what we say, f dash of x. So it's like an apostrophe above the f, okay? Above my function. So this is what I'm going to work out. This is what I call my derivative, okay? Derivative. This is going to be then another function of x, right? As I said, it's going to be a gradient function, okay? So it's going to be a gradient, which is also a function in terms of x. So that's how we notate it, right? That's how we express the derivative or gradient of a function. So if I have a function, then the gradient function or the derivative will be marked by this apostrophe here. Therefore, I can say f dash of x is equal to my gradient expression here. If I were to continue on with this then, well, it'd be limit as h tends to 0, but instead of f of x, I have f of x plus h. My input is x plus h. Well, f of x is x cubed, so f of x plus h is going to be x plus h cubed. Then take away f of x, well, f of x is just x cubed. And then it's all over h. And so then if I continue this, then limit h tends to 0, then I need to expand this bracket here, okay? So it's a triple bracket, so it's probably best to do it somewhere, let's say here. So x plus h cubed is going to be x plus h 3 times. So if I was to expand this then, well, firstly, x plus h times x plus h, that's going to be x squared, add 2hx, add h squared, then that's times by another x plus h. Then if I expand this, I would get x cubed plus hx squared plus 2hx squared, right? So remember here, 2hx times x, that's 2h times x squared, okay? Make sure you're very confident with being able to expand, alright? Don't get lost in the algebra here. So it's going to be 2hx squared, then 2hx times h will be 2h squared x, right? Then h squared times x will be h squared x. And then h squared times h will be h cubed, okay? And actually we can simplify, we can collect some like terms here. So you have an x cubed, and then we have, then we can collect this like term, right? hx squared, then we have 2hx squared, so that's 3hx squared, right? Then we can also collect the h squared x term here. So 2h squared x and another h squared x will be 3h squared x, okay? Then we got an h cubed, and that's there, and then that's simplified. So now we've expanded this bracket, we can substitute this result into here, right? Into here. So then x plus h cubed, that's going to be x cubed, add 3hx squared, add 3h squared x, add h cubed, take away x cubed, all over h, right? And then again I can simplify the top because the x cubed will cancel, so I'm left with 3hx squared, add 3h squared x, add h cubed over h. And then I can and then notice all the terms on the top will have a h in common, so I can factor a h out. So it's going to be lim as h tends to 0. Then if I factor a h on the top, I get 3x squared add 3hx add h squared all over h. And then again I can then cancel the h out. So I'm left with limit as h tends to 0 of 3x squared add 3hx add h squared. Okay, obviously I can't do anything more with that, but then I can sort of see what happens when h is going to 0 by basically just seeing what happens when h is 0. Okay, so if I do that, then as h is 0, then the expression becomes 3x squared add 3 lots of 0x add 0 squared. Obviously, again, let's just leave it. We can let's leave the x alone, right? But we can deal with the h. So I plugged in 0 into h here because that's when h is going to 0. Well, then I get 3x squared, but then 3 times 0, but that's just 0, so that goes away. As does this. That all goes to 0, and this is my final expression. So my final expression for the gradient function, or the derivative f dash of x, is this. And so there we are. I've shown that the derivative is 3x squared, okay? And so again, you can see then it's a function, right? My gradient, or my gradient function, is also in terms of x. And the idea is then, this is why this method is so powerful, is because instead of just obviously from GCSE, you'll just be used to basically, say for example I had a point here, you'd probably just draw a tangent line, right, at that particular point. And let's say though you wanted to find multiple points and their gradient. Let's say we had a point here, here, and here. You'd have to draw 4 different tangent lines, use square graphing paper to estimate the gradient. It's a lot of work, right? But the whole idea with this idea is that first of all it gives me just the fully accurate answer, right? It's fully accurate. There's no estimating, but also I can just plug in values of x, right? So if I then plugged in f dash of 0, the gradient would be 0. 3 times 0 is 0. So immediately that's telling me at 0, the gradient is 0. Then if I plugged in f dash of 1, that's 3 times 1 squared, which is 3. And then you notice I can just plug in many values of x to quickly tell me the exact gradient at that point. So it's a very superior method to just using tangents, okay? Okay, cool. And so therefore it's a gradient function, because now the gradient will be a function of x. So then I can substitute values of x to get the gradient at that point. Okay. Right. So we've got some exercises then, and we're going to continue with this. It's a sort of common exam question. It's easy mark, so we want to try and practice this. So we're told now to prove from first principles that the derivative of 6x is 6. So again, in general, the gradient, right, the derivative is f dash of x is given to be f of x plus h minus f of x over h. That is again the standard formula from the formula book. But again, what's my function? It's 6x, right? So therefore, if I use this function here, my gradient, it should be limit as h tends to 0. My apologies. Yeah, do not forget that bit as well. It's when h tends to 0, right? Okay, so my function is 6x, so f of x plus h is going to be 6 lots of, so lim as h tends to 0, of f of x plus h, which is 6 lots of x plus h. Right, remember, because I'm changing my input, it's not x, it's x plus h into here. Then minus f of x, that's just minus 6x, all over h. Right, cool. Okay. But then I can expand this bracket, right? So lim as h tends to 0 of 6x add 6h minus 6x all over h. Okay. And so then I can cancel out the 6x's here, right? So I'm left with lim as h tends to 0 of 6h over h. But then the h's cancel, right? So I'm left with lim as h tends to 0 of 6. Well, actually then there's no h, so in actuality h is gone, so it's just 6, okay, as a result. And there we are. So that means my gradient is 6, and actually there's no x, so that means for any value of x, right, like for any value of x, the gradient would always be 6. And no matter what value of x I plug into here, I will always get 6. And that makes sense, because think about it, 6x, right, if I said y is equal to 6x, and then if you remember y is mx plus c for a line, m's the gradient, so m would always be 6, so the gradient will always be 6, which makes sense with my answer then, right? The gradient is 6. Okay, okay, now we've got this question then. So now I'm told f of x is equal to ax squared, right, for some number a. Prove from first principles that f dash of x is 2ax. So again, I'm going to do the same approach. So remember, f dash of x then, via the formula, is limit h tends to 0 of f of x plus h minus f of x over h. And so then if we then use our function here, well, f of x plus h will be a lots of x plus h squared minus f of x, that's minus ax squared, all over h. So then we need to expand this bracket, right? X plus h squared. If I do that here somewhere, that would get me x squared add 2hx add h squared. So then I can substitute that in, right? So then my limit as h tends to 0 of a lots of this. So it's going to be a lots of x squared add 2hx add h squared minus ax squared all over h. And then I can further expand this then, right? Then I'm left with lim as h tends to 0 of ax squared add 2ahx add ah squared minus ax squared all over h. And then again, likewise for the other examples, the ax squareds cancel. I can then simplify further to get lim as h tends to 0 of 2ax or 2ahx add ah squared over h. And I notice h is a common, and a is a common factor as well. I can pull out a factor of ah, right? Of ah, lots of 2x add h all over h. And then I can cancel the h's out, right? To be left with, as h tends to 0, of a lots of 2x plus h. And then if I expand that out, I get 2ax add ah. Okay, that's my final expression, right, after simplification. But again, now we're going to look at what happens when h is pushed to 0, right? When h tends to 0, well, what happens when h is 0 then, right? So it's going to be 2ax add ah, so h is basically 0 then. So then that just leaves me 2ax. So therefore, the gradient function f dash of x is 2ax. And there we are. So we prove that the gradient is 2ax. Okay, cool. So hopefully you start to get sort of an idea of the recipe now for this sort of problem. With first principles, we use this fraction, and then we just sort of substitute stuff in, right? Our function in, expand some brackets, and then cancel some stuff out. Okay. We've got this question then, which is now a tad bit different, but it's just going to be the exact same idea still. But we are told now we have a point A with coordinates -1, 4, which lies on the curve with equation y is equal to x cubed minus 5x. The point B also lies on the curve and has x coordinate -1 at h. First of all, it says to show that the gradient of the line segment AB, so from A to B, right? The gradient is h squared minus 3h minus 2. Okay, so basically it's asking for the gradient of AB, right? So between points A and B, well, that's going to be changing y, changing x, but we need to know what our points are. Well, A, we're told is minus 1, 4. What about B? Well, B, we're told the x coordinate is h minus 1. Okay, but what about the y coordinate? We don't have the y coordinate, right? But we're told the curve. The curve is y is x cubed minus 5x. Well, then I can substitute my x coordinate in to find y, right? If I do that, then I get that y is going to be, well, instead of x, it's going to be h minus 1. So h minus 1 cubed minus 5 lots of h minus 1. And then it just becomes an expanding bracket exercise, right? So if I expand this, well, firstly, I'm going to do that somewhere. I'm going to do it over here, right? H minus 1 cubed is going to be h minus 1 3 times. So if I do this, then, well, if I expand the first two brackets, that's going to be h squared minus 2h plus 1 times by h minus 1. Then if I expand that, then I get h cubed minus h squared minus 2h squared plus 2h plus h minus 1. And then I can further simplify by collecting like terms. So h cubed, then minus h squared minus 2h squared will be minus 3h squared plus 3h minus 1. Okay? Cool. So then I can substitute this into here, right? So h minus 1 cubed is going to be h cubed minus 3h squared plus 3h minus 1. Then minus 5 lots of h minus 1. If I expand that bracket, then it's going to be minus 5h, add 5. And then again, I can further simplify this. So I'm going to get h cubed minus 3h squared. Then 3h minus 5h will be minus 2h, right? Then minus 1 plus 5 will be plus 4. And there we are. So then my y coordinate, so then B have the coordinate h minus 1, h cubed. Actually, I'll write it up here somewhere. Hang on. So my coordinate would be, oh, here, right here. So h minus 1 for x, and y, as we've seen here, would then be h cubed minus 3h squared minus 2h plus 4. So then the gradient from A to B is again changing y, changing x. Right? Well, changing y, well, at B, y is h cubed minus 3h squared minus 2h plus 4. And then y at A is 4. Okay, so take away 4 over changing x. So then at x, B is h minus 1. Take away minus 1. But the problem is then that'd be a double negative, so that'd be plus 1. Okay, so then I'll just need to simplify this. Well, firstly, 4 minus 4 on the top will cancel, so I'm left with h cubed minus 3h squared minus 2h plus, that's it, minus 2h. These two will cancel. Over h minus 1 plus 1 will also cancel, so it's just over h. And then I can factor a h out, right, on the top. I'm going to need to get rid of this bit now. So I can factor a h out on the top there. So if I do that, then I get h of h squared minus 3h minus 2 divided by h, and then the h will cancel to be left with h squared minus 3h minus 2. And there we are. That's part A done. We've shown that the gradient goes to this h squared minus 3h minus 2. Then part B then says deduce the gradient of the curve at A. So the gradient of the curve at A is going to be the same idea then as h is pushed to 0, right? So that means as h goes to 0, then this expression, the gradient, well, that goes to, well, h squared would be 0 squared minus 3 lots of 0 minus 2, but then that goes to just minus 2. Okay, so therefore the gradient then at A is minus 2. And there we are. Cool. Okay. Okay, so we're going to finish off a bit with an exam question then. And you can see the exam questions are usually the same sort of question on this topic. They very rarely deviate from this sort of style of question. So once you can get the sort of method down, you should be fine. Okay. Okay, so we're told that y is equal to 2x squared. Then we need to use differentiation from first principles. By the way, differentiation, obviously the topic name, differentiation is basically the study of gradients, essentially. So differentiation means, well, gradients, really. So differentiation from first principles, we're basically finding the gradient from first principles, which means we will be using the formula f dash of x is h tends to 0 of f of x plus h minus f of x over h. We're told to use first principles to show that, okay, this expression here, dy over dx is equal to 4x. Now, I already spoke about this notation here, f dash of x or f apostrophe, or f with this apostrophe, meaning the gradient function or the derivative of the function, right? So it tells me the gradient of my function. This notation here, dy dx, is the same thing. We can use either f dash of x or dy dx. They're the same thing, but written in different ways. But they both mean gradients. They're both gradient function. Okay. So we will be seeing this notation, but they mean the same thing. You can either use f dash of x if you have functions, or dy dx. Okay, it's completely up to you. But they both just mean the gradient. Okay, so effectively we need to show that the gradient of 2x squared is 4x. So we're going to use this formula again. Okay, this formula again. So firstly, if y is 2x squared, well, firstly we can use functions, right? We can also say f of x is 2x squared, right? Therefore then, f dash of x, if I use my formula here, that's going to be the lim as h tends to 0 of f of x plus h. Well, f of x is 2x squared, so x plus h will be 2 lots of x plus h squared. Take away f of x, so take away 2x squared. If I do that, and then all over h, and then if I do that, well, I'm going to need to expand this bracket, right? So this x plus h squared, so that's going to be 2 lots of, then if I expand this, I get x squared, add 2hx, add h squared. Remember, you can expand it to the side somewhere. If you really want to do it step by step, if you're not comfortable, you can expand that bracket step by step somewhere else, and then you can plug that back into here. But if we expand it, we get this result, okay? Then we take away the 2x squared. Then we can all over h. And then we can expand the 2, right? Expand this bracket we've got here. So then 2 times x squared. And then 4hx plus 2h squared. Take away 2x squared all over h. Well, then the 2x squareds cancel. And then I'm left with 4hx add 2h squared over h, and then again I can factor a h out. I can factor a 2 out as well, actually. 2h of 2x add h all over h, and then I can cancel a h out, it's a common factor. So then I'm left with lim as h tends to 0 of 2 lots of 2x plus h. And then if I expand that, I get 4x add 2h. Okay, so then at that point, then I can consider pushing h to 0. So h goes to 0. When that happens, we get 4x add 2 lots of 0. But the 0 cancels and I'm left with just 4x. So therefore my gradient, dy dx, or f dash of x, no matter what you use, dy dx is now 4x, and there we are. Cool. Cool. So there we are. And just a final note then about this h tends to 0 business. As you can see here, we effectively at the end step, right, we effectively have sort. We see what happens when basically h is 0. That's the whole idea, right? When h is pushed to 0, then we see what the expression is, and that's my gradient. But you might be thinking, well, what if I just substitute h is 0 right away? What if I just plug in h into this expression here at the start, this whole fraction? But then what happens is h goes to 0. Okay, but then you're dividing by 0, so that won't tell you anything about the gradient. Okay, it's undefined if you substitute it early on. It will not tell you anything about the gradient. Okay, so you need to be very careful with when you plug in your h is 0. Usually you should only do it at the very end. Okay, if you do it too early, if you're dividing by h, if you divide by 0 again, you've probably done something wrong. Okay, usually with these sort of questions in this course anyway, you should only consider h going to 0 at the very end. Okay, then h goes to 0, then you get the final answer. Okay, you should never try and divide by 0. Okay, never ever divide by 0. Try and simplify first before you try and divide by 0. Okay, okay. So that's it for this section, but I'll see you next time.